Hello, this is a summary of what we did in class on October 13th, 2020 via Zoom. And really what today was about was how do we deal with multiple forces? So at the end of the day, usually more than one thing is pushing or pulling on an object, and we have to find a way to see how those effects combine. So we'll take a look at the notes. I started with this picture. I've got two stuffed angry birds here. One's flying through the air, one's sitting on a desk. They clearly don't have the same acceleration. Hopefully you remember that the one flying through the air has an acceleration of 9.8 meters per second downward, whereas the one sitting on the desk, it's sitting there. It has no acceleration. So clearly the force of gravity is not the only thing that's happening here. But we have this equation F equals ma, and the point is when you're trying to figure out what the F is that goes in that equation, what is the force, it can't just be one force. It has to be the effect of all of the forces on an object. So this angry bird is not accelerating like the other one is because it's not alone in having gravity. It also has a force from the desk, or a normal force. And we have to combine those two effects. The way we combine them is we come up with a total force, which is also called a net force. And it has the abbreviation sigma F. This is the Greek letter sigma. Whenever you see it in math and science, it means you're adding stuff up. So in this case, in order to calculate an acceleration, we're going to add all our forces up. So we'll take a look at this angry bird. And we'll figure out what its total or net force is. We'll come back to this one later because we learned something about it as well. So in the case of this one, the net or total force equals mass times acceleration. You replace this term sigma F with basically your list of forces. You have to decide what direction you're calling positive and which one you're calling negative. I'm going to call the upward forces positive, the downwards negative in this problem. And that means my normal force from the desk is an upward positive force, and my weight or gravity is a negative force. And that's how we can have no acceleration. The upward force is entirely canceled out by the downward force. So at the end of the day, we have to get good at keeping track of what forces are on various objects. So what we'll do as we work through these problems is we'll try to draw pictures that have the various forces on them, and we'll use the forces from the picture to determine what the sigma F or net force equation is. So that was kind of the first thing we did today. I had students work on a worksheet called Free Body Diagram Practice. And they basically went through and determined what force picture they should draw for each of these situations. In this video now, I'm going to go through the answer key for this. You should try this before you look at the answer key. So the reason I have these three grouped together is they're actually almost the same question. Here's the answers. And at the end of the day, we don't care whether a force is a push or a pull. It's a force. So in questions 1 or 2, the two people are accelerating the box to the left. So their forces are the same in each case, even though in one case they're pushing and the other case they're pulling. Notice that the up-down forces in this case just cancel each other out. In this whole unit, we may have up-down forces or y-axis forces. We may have left-right forces or x-axis forces. One of those two dimensions will always cancel out in this first unit. So we're only really going to be solving problems either left-right or up-down. Question 3 is basically the same problem, except now we add another force, a friction force on there. And notice it's less than either of the two original forces, so I drew the arrow smaller. So those are the answers for the first three. Notice I did not draw anything that looked like this where I tried to distinguish between a push or a pull. That can get confusing really quickly. At the end of the day, we're using these pictures to determine in what direction is the force unbalanced, and we should start all forces from the middle. So in this question, it says one kid pushes from the left, one kid pulls to the right. Those are in the same direction. So we just show that the two are helping each other. 4, 5, and 6 is another set of related forces. 4 and 5 are basically the same question. Someone's at rest, someone's moving at constant velocity. As we've seen, there's no difference between objects in motion and objects at rest. Neither requires a force. You only need forces for changes in velocity. So the answer to the first two questions is identical. They have canceled out vertical forces and no horizontal forces. We call a situation where all your forces cancel equilibrium. And that means all your forces are balanced. And when you're in equilibrium, you have no acceleration. You can make a distinction between this one where the person's in motion, this one's not in motion. We could call at rest static equilibrium, in motion dynamic equilibrium. But the key idea is that in both cases, you have no acceleration. And we know that the difference between these two physically is perspective. If you had a camera on a skateboard moving at the same speed as this one, this person would look like they're at rest. In the third question, though, there is an unbalanced force. The person's slowing down, and that's the friction force. And that's opposite the direction of velocity. So in that case, we will have an unbalanced force. I think this was the trickiest question of all of them. And the basic way you do it, you draw the ramp, and we see that we have a downward gravity force because they're being pulled towards the center of the earth. The normal force is always perpendicular to the surface you're on. So the normal force in this case is off at this angle. In fact, that's what normal means. It's a synonym of perpendicular. If I just had the red and blue forces here, if you could imagine two ropes pulling this person, they're generally going to be pulled towards the left here. So there must be some force holding them on the ramp. And that force is friction. You can imagine someone standing on an icy ramp, they're going to go sliding down it. So we need an upward force to cancel out those two forces. Here's another pair of problems that I think are helpful for students to think about. A person standing on the ground versus a person falling and hitting the ground. Those are actually the same question again in some ways. There's a downward gravity force and an upward normal force. And in the case of someone standing on the ground, they're in static equilibrium, the forces are balanced. If the person is currently hitting the ground, they're not in equilibrium because they were moving down and the ground is stopping that. So there must be a bigger upward force. That's why it doesn't hurt to stand on the ground. The normal force there is just equal to your weight. But if you fall and hit the ground, it does hurt because the ground is pushing you with more of a force to bring you to rest. The last question was about an accelerating car. And in general, we have some backward forces like wind resistance and stuff. And if we're accelerating forward, then the tires must be pushing the road with a larger force. And that's actually a frictional force, the friction between your tires and the road. So these force pictures, they're absolutely crucial for solving problems. And basically, in all of these problems, you're going to have a set of information. You're going to have to draw a picture, make this force picture, and that's what's going to help you figure out sigma F equals ma. There was one other thing we did today before we started solving these problems, and that was we looked at the angry bird that was in the air. And we can actually figure out something from its sigma F equation. Sigma F in this case, the net force, is just the gravity force. Notice I'm calling down positive here to make the problem easier. So I replace sigma F with the one force, gravity. It still equals ma. We know when something's flying through the air, the acceleration is 9.8. So that means that the weight, the force of gravity on something, must be its mass times 9.8. And we abbreviate that as Fg, the weight, the force of gravity, equals mg. So anytime you're looking at the force of gravity, you can calculate that by just doing mass times 9.8. What I did next was an example problem, and I have a YouTube video of that posted, and I'll put a link for it right after this video. So if you want to pause this video and watch that one now, you can see how to do those example problems. Then I had students work in groups to answer these questions. And you will have an answer key available to you for all these questions as well. And like I just showed in that YouTube video, the basic way we solve these problems, we draw a force picture. We do sigma F equals ma. We replace sigma F with whatever the forces from the picture are. Notice in this picture, I'm only looking at the forces that are left, right. I'm not looking at the ones that are up, down. In general, we treat up, down, and left, right separate, and we're only going to look at one set of them in these problems. So I ignored up, down entirely, and I just looked at left, right. In general, there'll be a sigma F equals ma equation. There'll be a motion equation. Which one you do first is going to depend on the problem. And don't stress on it. Just start doing one of them, say the sigma F equals ma one. If you get stuck with something unsolvable, like an unknown force and an unknown acceleration, just pause and do the motion part. In general, whichever one you do first, you'll take A and you'll plug into the other one. So in this case, we solved this first, took A, plugged in over here. This is one of the trickiest things we do in the whole fall semester. It's going to take some practice, and it's going to take learning how to be organized on these. So if you're struggling with these, don't think it's something you can't do. I am here for you to help you figure out organization. And ultimately, after you do a bunch of these, you'll be feeling a lot more confident. But please be in touch as you work through these, because I do want to help. Thank you. Make sure to watch that example problem I posted on YouTube.